and then we will just go for one or two more problem, and then we will go for basically formulation of Lagrangian. Okay. So what is the problem? Problem was very simple. There is a table, and there is a hole on a table, and the particle M1 is attached to end of a massless string, and another particle which is attached to another end of massless string. This is M1 and this is M2. And what we have to do? We have to just calculate the degree of freedom. And what is the story? The story is that particle M1 is constrained to move on a surface of table, and particle M2 can move in vertical direction. So it can move up or down as M1 will go towards the hole or away towards the hole. If M1 will go towards the hole, then M2 will go away the hole. If M1 will go away the hole, then M2 will go towards the hole. Okay. So this is a beautiful story. Let's try to figure out what is the degree of freedom and how we can find the and how we can write the equation of holonomic constraint. So once we are able to write the equation of holonomic constraint, then each and everything is very easy for you. And we can also try to understand that for which coordinate system is much more efficient to understand to analyze the system. These all can be explained by the basically equation of constraint. So straightforward. First, what I will do, I will just keep this mass free and this mass free. I can take this as my origin. So this is my origin. If this mass will free, I can give a Cartesian coordinate as x1, y1, z1. One is for the first mass. And for the M2, I can give the coordinate, and that coordinate is x2, y2, z2. But the story is not so simple. Both particles are not free. There are n number of story as related to M1. There are some story are related to M2. There are some story related to M1 and M2. So let's try to go for M1. So I can say this is nothing but my xy plane, the surface of table. This surface of table, the particle is just moving on this particular surface of table. This is your xy plane. And this vertical direction of the table, suppose this is table and this is your vertical direction, this will be your z-axis. Okay. So for first particle, what is the constraint? The particle is confined to move on xy plane. It will not go into the z direction. That means z1 must be equal to 0. Okay. For the second particle, it is just moving in only in z direction. So what is meaning of that? Meaning of that, x2 is equal to 0 as well as y2 is equal to 0. Is that only this is a story? This is a story for M1. This is a story for M2. Now we have to go for a story for M1 and M2. Is that motion of M1 and motion of M2 are independent or dependent? Dependent. Why they are dependent?
They are bounded in a string.
Yes, because this length is fixed, isn't it?
Yes, sir.
This length is fixed because they are attached to end of massless string. So this length is fixed. So yes, we have to use the distance formula. So what is this distance? This distance is nothing. x1 minus 0 whole square plus y1 minus 0 whole square root under plus, what will be this distance? This distance is nothing but z2 minus 0 whole square root under is equal to L. Yes? Okay. आप अपना म्यूट करके रखो, जब आपको जरूरत होगा तो आप अनम्यूट करोगे. ओके. सो अदरवाइज देयर आर लॉट ऑफ नॉइज, है ना? सो व्हेन यू आप साथ साथ बोलते रहो बट म्यूट करके बोलते रहो. ओके. सो if you have any doubt, then you can unmute, or if I will ask then you have to unmute. Okay, good. Thank you. So how many equation of constraints are there? 4 equation of constraints are there. This is first one, this is second one, this is third one, and this is fourth one. How many number of particles are there? n is equal to 2. And yes, we have to go for n 3 into 2. If the particle would free, all these two particles would free, then there is 6 degree of freedom. But there are 4 constraints, 4 different story that will tell you all about that. Due to this story, some motion are not going to occur. And that value is -4. So we have 2 degree of freedom. How many degree of freedom is there? There is 2 degree of freedom. Now you can see this particle is moving only along z direction. M2 is constrained to move only along z direction. So which coordinate system is suitable for M2? Anybody can give me answer?
Cylindrical.
No, why it is cylindrical? Because this is just a linear motion.
Spherical polar, sir.
Why spherical polar? That is a Cartesian coordinate. The particle is just moving along a line. Why you need a sphere? Why you need cylinder? If it is just moving along the line, that's it. It is a Cartesian coordinate for M1. Now, just tell me, can you visualize this equation? इस equation को visualize कर सकते हो? Can I write this equation as x1 minus 0 whole square plus y1 minus 0 whole square is L minus Z2 whole square. Can I write this thing? Yes?
Yes, sir.
Yes. So what is this equation?
Equation of circle.
That is equation of circle. Very good. Where is the origin? Where is the center? Where is the center? Not origin. Where is the center? At the 0, 0.
0, 0.
At the 0, 0. And what is the radius?
L minus Z2.
L minus Z2. Is that radius is fixed or changing?
Changing.
Changing. So it is a moving on a circular symmetry where radius is going to change. Are you going my point? You can see this whole story from this equation, isn't it? In this equation, you can easily say that the radius of particle is going to change, but it will just move something like as a circular symmetry. So for first mass M1, which coordinate system we have to go? Circular polar. And for second mass M2, which coordinate system we have to go? We have to go for directly Cartesian, but a story is much more. The story is much more. We will discuss after some time. But before that, let's go for one more problem.
Sir, what you said in the last, please repeat that. You were frozen by my time.
I could not remember what I have said. Where is the problem? You can just ask. Okay. Because this is just a extempore, okay?
Okay.
Okay, you can ask if you have any doubt, you can ask. I don't remember what I have said earlier.
Sir,
okay.
After this last equation, what you were explaining, please repeat that.
For this equation, I am saying that M1 is moving in a circular symmetry because this is equation of circle, and that circular symmetry have radius that is going to change. Okay?
Okay.
Okay. So let's try to go for one more problem. Then we will go for generalized coordinate and generalized velocity. Okay. So there is a mass, and this mass is M1, and it is attached to a massless rod, and another end is M2. And you can say something like this, and it is your x direction. So M1 is constrained to move in x direction. M1 is constrained to move in x direction, while M2 is constrained to move in xy plane. M2 is constrained to move in what? XY plane, XY vertical plane. So we have to find degree of freedom. Okay. Now, how many particles are there? N is equal to 2. Now, where should be origin? Should I take this as a origin?
No, sir.
No. Why? Because it is moving. Okay, so
Moving.
origin must be fixed point. So there is not any another point. I can take this as my origin. If this particle will free, I can take x1, y1, z1. 1 is a suffix for the first particle. And if this particle is free, I can write x2, y2, z2. But this is not a story. The story is entirely different. The M1 is constrained to move along x-axis. What is meaning of that? Mathematically, how you can translate this particular thing?
y1 equal to 0. Z1
Exactly. Y1 is equal to 0 and Z1 is equal to 0.
0.
Exactly. Very good. Now M2 is constrained to move in XY plane. What is meaning of that?
Equal to 0.
This is very good. So this is a story for M1. And let's try to go for a separate story for M2. What is the story for M2? That M2 is just moving on a surface of, on a plane. And what is this value? That means Z2 is equal to 0. Is that only a story? Or there is more, any more story?
Yes, sir.
What is that story?
Length of the string.
Yes, you can see if this particle is moving, this particle is bound to move with this particle, isn't it?
Yes, sir.
Why it is bound to move? Why? Why? Because they are attached to end of this massless string or this massless rod. You can just assume this is massless rod. So hence this length is always fixed. Then obviously there is one more constraint. The motion of M2 and the motion of M1 is not independent, rather they are dependent, at least in a linear sense. So what is going to happen? I can write x2 minus x1 whole square, y2 minus 0 whole square must be equal to L square. Are you people happy?
Yes, sir.
Yes. This is distance formula. I have just make it square. Now, just tell me, for M1, which coordinate system you prefer?
Linear. So
Linear. Cartesian. Very good. Very good. Now look at M2 very carefully. What is the coordinate of M2? What is dynamical variable associated to M2? X2 and Y2. So just look at X2 and Y2. Which symmetry it is following? Circular. Are you getting my point? Circular symmetry. But in that circular symmetry, is that radius is fixed or variable?
Fixed.
Fixed. Radius is fixed. L is fixed.
Okay.
Is that center is fixed or variable? Variable. X1 and 0. X1 itself is changing with the time. So center is going to vary. So you have to try to figure out that circle whose center is at x1 and 0 and radius is L. But by the way, we will discuss all this thing when we are going to solve the problem. But by the way, how many constraints equation are there? This is my first one. This is my second one. This is my third one. This is my fourth one. Then we have 3 into 2 minus 4 is equal to 2 degree of freedom. So how many independent motion can be possible?
2.
2. Because degree of freedom is equal to what? 2. Okay. So we will solve a lot of problems when we will solve the Lagrangian, but without finding the degree of freedom, you cannot solve Lagrangian of a system. Why? Let me discuss in the next section. Okay. चलते हम लोग next section में, and where we are just going to understand what is generalized coordinate, what is generalized velocity, and then we will just go for a very basic mathematics, which is the base of your classical mechanics, and that is nothing but variational principle. Okay, or for calculus of variation, not variational principle. That is what? Calculus of variation. So let's try to go for this. Okay, good. I will give you one more problem for degree of freedom. You have to post me. Okay, so take homework. Post करोगे कि नहीं करोगे तो फिर मैं क्लास नहीं लूंगा. Okay, so this is your double pendulum. This is your double pendulum. This is mass m1. This is mass m2. This is length l1. This is length l2. This is x. This is y. So double pendulum, both mass m1 and m2, m1 and m2 constrained to move in xy plane. You have to find degree of freedom. This is your homework. I expect all the people, all 19 में एक तो मैं हूं. So at least 18 people or 17 people have to give me this solution. Please do it. Okay, it is my request to you. Okay, let's try to go for a generalized coordinate. Generalized coordinate. In general, we give the notation of generalized coordinate is something like qi. What is the notation? That is something like qi. Okay, what is generalized coordinate? So generalized coordinate qi, it's some dynamical variable some dynamical variable which can explain independent motion of a system uniquely, which can explain the motion of a system uniquely. Okay, and which type of motion? Independent motion, which can explain the independent motion of a system uniquely, which should explain independent motion of a system uniquely. Okay, so this is all about generalized coordinate. And please mind it is always a dynamical variable. That means qi dot is equal to not 0. And it is not necessary that dimension of each generalized coordinate of a system is dimension of length. It is not necessary. So in a same problem, you can have two different generalized coordinate, and one generalized coordinate can have some dimension and another generalized coordinate can have another dimension. You can have these leverages. So why it is identified as generalized coordinate. But what is fundamental? The fundamental is very interesting. The fundamental is that this must tell you all the independent motion. So what is associated with the independent motion?
Degree of freedom.
Degree of freedom, exactly. So if I am talking about independent motion, I am talking about degree of freedom. I am talking about degree of freedom. So what you have to always do this, what you have to do, you have to always go for a very nice litmus test, and that litmus test is nothing, but you have to always check if number of generalized coordinate equal to or number of dynamical variable, you have to write this thing. This will be much better. So what you have to do, if you have number of dynamical variable must be equal to number of DOF, then this dynamical variable can identified as generalized coordinate. And this generalized coordinate will tell you all the independent motion. Means if something is doing a circular motion, then obviously there must be some angular dynamical variable must be there. Some angle must be treated as your dynamical variable. So it's a very interesting. So always you have to choose that you cannot choose arbitrarily any dynamical variable and you can say that, okay, this is my generalized coordinate. What you have to do, you have to always first calculate what is your degree of freedom, and then for each degree of freedom, which is the suitable coordinate, you have to identify. And in this finding the suitability of a coordinate, you have to just talk about you have to just see the configuration of a system. What is the configuration of a system and how this configuration will help in a motion or restrict the motion? That both the thing can be discussed by degree of freedom, isn't it? Because when we are going to calculate the degree of freedom, we are actually talking about the independent motion, but same time we are also talking about what are the constraints. So it's a very interesting point. So whenever you are going to solve the problem, you always check, is that your number of dynamical variable is equal to number of degree of freedom? If yes, then you can go for generalized coordinate. Okay. Now we will go for what? Generalized velocity. So let's try to go for generalized velocity. If Qi is generalized coordinate, then look at the wording. Wording is very important. Then generalized velocity, GV is what? Generalized velocity conjugate to generalized conjugate to Qi is Qi dot, and this is dQi upon dt. This is identified your what? Generalized velocity. This is identified generalized velocity. So what is the dimension of generalized velocity? That will depends on what is dimension of generalized coordinate. So suppose the dimension of generalized coordinate, suppose I have the dimension of generalized coordinate is a dimension of momentum. Then what will be your generalized velocity? Then what is your generalized velocity? Force. Obviously, this force is your generalized velocity. Suppose you have dimension of generalized coordinate is angular momentum. Then what is your generalized velocity? Then this is nothing but torque. Because you are not restricted to length as your generalized coordinate. Even you have one generalized coordinate as length, another generalized coordinate as angle. Then what is your generalized velocity for the length? Conjugate to length is your meter per second. that is length by time. But when you are talking about angle, then what will be your generalized velocity? That means frequency, isn't it? Theta dot is nothing but the dimension of frequency, 1 upon time. So you are now working generalized in a generalized sense. You are not restricted yourself that only you have to go for Cartesian coordinate or something like that. And you will be very surprised that for one particle, you can just go for Cartesian coordinate, and for the another particle, you can go for a circular polar coordinate. And for the whole system, the first generalized coordinate is x and second generalized coordinate is theta. It may be possible. You will see. The thing is that whether we have taken this dynamical barrier are able to explain independent motion of a system or not. And why we are using the word uniquely? Uniquely means if qi or q1 is one generalized coordinate, it must explain or it must associate it about with one particular degree of freedom. And if q2 is another generalized coordinate, that must associate it with another degree of freedom. So you cannot say this x or q1 will explain these 2 degree of freedom because both are independent. So we have a unique nature of motion because motion are independent. So you have one unique quantity and that is associated to one generalized coordinate, one unique quantity that is associated to one generalized coordinate. So it's a very interesting. But all of this particular point, this is one of the most fundamental point, that number of degree of freedom must be equal to number of number of dynamical variable. You have to always check. You have to always check. So again, if I will ask you, what is the most important point in the Lagrangian formulation?
Equation of constraint.
Exactly. Very good. Excellent. Degree of freedom is just an outcome of writing the equation of constraint. So we have to always try to focus ourselves how we can write equation of constraint. Are you people happy up to this point? Let's go for a very fundamental mathematics behind the all formulation of classical mechanics, mainly the Lagrangian formulation. Once we will have Lagrangian formulation, we can easily go for Hamiltonian and all other formulation. But let's try to go for a very fundamental thing that is all about your calculus of variation. And this is not maybe not part of your syllabus, but yes, we have to use it. And it's a very fundamental mathematical technique where you can optimize any path, any shape. So let's try to go for one basic problem and let's see first what is calculus of variation. So let's try to go for calculus of variation. Calculus of variation. Let's try to go for this. What is this calculus of variation? Suppose we have any integral and that integral is a function of y, y dot and x dx, where y can be function of x and y dot is actually dy upon dx. Okay, I have defined something like this. So don't confuse that y dot is dy upon dt. Okay, dy upon dx. X can be any variable, don't worry. Now, this is one integral. What I want to do, I just want to make this thing optimize or extremum. So what will happen if we are just talking about extremum? Then obviously this del, or which is equivalent to del of this y f y y dot x dx must be equal to 0, because always extremum means I am talking about either maxima or minima. Are you people happy? So this is your del I, and del is f y y dot x dx is equal to 0. Great. So if this condition holds, then this f will follow f as a function of y, y dot x will follow Euler Lagrangian equation. This f will follow what? Euler Lagrange equation. And what is this Euler Lagrange equation? The Euler Lagrange equation is d upon dx del f upon del y dot minus del f upon del y must be equal to 0. This is all about Euler Lagrange equation. So from here you can find what is the nature of path and all this thing. So we will just try to understand how we will apply it on one particular problem. So don't think that this type of question will come into your exam. So this is not for your exam, but this is a basic mathematics on which a Hamilton's principle are going to derived, and then only Lagrangian formulation is there. So let's try to go for one basic problem. So let me ask you a question. What will be the shape of shortest path in a plane? Straight line. Everyone knows that this is nothing but what? Straight line. So let's try to prove it with the help of this particular calculus of variation. What we have? We have a x and this is y. Suppose this is my first point and this is my second point. And I can go with this path, and I am taking this as my ds. ds is what? The ds is all about the curve, and ds, if I am going to integrate this ds, I will get the whole curve s. So what I have to do, I have to optimize this curve, and this is my first point and this is my second point. So we have to go from 1 to 2. Now, how I can write this particular ds? Suppose I am just making the little bit zoom diagram for you. Is that this value is dx and this value is dy? And for ds tends to 0, or dx and dy tends to 0, this will almost a straight line. Calculus, you remember all this calculus, isn't it? Because this is elemental length, okay? And this elemental length I can write as something root under dx square plus root under dy square. We have to go for 1 to 2. Sorry, 1 to 2. Are you people happy? Yes? Now, let's try to go for this integral. Can I write this will be dy upon dx whole square into dx, and we have to go for 1 to 2. Okay. Now, what is, and I have to optimize this particular s, है ना? इसी का तो एक्सट्रीमम चाहिए, मिनिमम लेंथ या मिनिमम पाथ, जो मिनिमम डिस्टेंस जो होगा वो क्या होगा इसके लिए? So we have to optimize this particular s. This is any particular length. This is any orbit length. So we have to just go for a minimum length, means I have to optimize this particular s. So when I have to optimize this particular s, let's try to go for a first derivative. So when we are going for the first derivative, then del s must be equal to 1 to 2 del variation root under 1 plus dy upon dx whole square dx. Now what is f here? What is f? What is f here? F is nothing but 1 plus dy upon dx whole square root under, and this is nothing 1 plus y dot square root under. If this is my f, this, and if it is going to optimize, that means this value must be equal to 0. That means this f must satisfy Euler-Lagrange's equation, isn't it? This f must satisfy Euler-Lagrange's equation. So what will be del f upon del y? क्या होगा ये? 0. Why? Because this f is not a function of y. Are people there?
Yes, sir.
Okay. So del f upon del y must be equal to 0. Let's try to go for del f upon del y dot. So I have to differentiate with respect to y dot. First I have to differentiate with the root. Then you have 2 y dot upon root under 1 plus y dot square, and half will be there. This and this will cancel out. That value is y dot root under 1 plus y dot square. Am I correct? Just do it with me. आप साथ साथ करते भी रहो. Then what will happen? D upon dx del f upon del y dot must be equal to 0. That means this quantity must be constant, isn't it? This quantity must be constant. So what will happen? Y dot root under 1 plus y dot must be equal to alpha.
Dot square, no, sir.
Sorry? Y dot square. Y dot square, obviously. Thank you. This is y dot square, and that must be alpha. What I am going to do, I will take it in this side and make it a square. So y dot square is equal to alpha square 1 plus y dot square. Okay. Now I am just taking y dot together. So y dot square is equal to 1 minus alpha square is equal to alpha square. So y dot square is equal to alpha square 1 minus alpha square, and y dot is nothing alpha square 1 minus alpha square to the power half. And constant by constant, I can say this is constant, isn't it? Yes. So I can say y dot is equal to some constant, because this is some constant value, and let's say this constant is m. And now what is y dot? Y dot is nothing but dy upon dx. That value is m. So what is y? Mx plus c. Look at the equation. What is this equation?
Straight lines.
Straight line.
Yes, yes.
This is nothing but what? Equation of straight line, isn't it? And you all know from your childhood, what is the shortest distance between the 2 points, between the plane, in the plane? What is that? That is nothing but what? Straight line. Okay. Are you getting this thing?
Yes, sir.
Okay. So now on to, and on this basis, you can find n number of problems. You can find n number of problems. But we are just going to focus on our main course structure. Okay. This is calculus of variation. This is mainly not in physics part. This is mainly mathematics. Those people who are doing the preparation for CSIR net from mathematics, they are using this technique very efficiently. Okay. So now on to basis of this particular story, we can go for Hamilton's principle. So let's try to go for what? Hamilton's principle. Or should I do it in the next class? So I think we have 10 minutes, so we can go for it, isn't it? Okay. So let's try to go for what? Hamilton's principle. What is Hamilton's principle? At least I must write the principle, and why, or at least I have to explain what I am going to do. And what is the challenge? That we have to give the answer. At least we have to discuss this thing. Now, this is very interesting. What we have? Suppose I have this chalk. And if initial condition is same and the environment is same and I am going to throw this chalk, what will happen? It will just go and come back. It has some unique path. Are you getting my point? Same time. You can see some unique path. Okay. Suppose I am going to throw this particular particle. Suppose I am going to throw this particular particle with some angle with the horizontal. Then it will follow the path of parabola. Okay. That is projectile. That is path of parabola. But look at the most fundamental question. The most fundamental question is that if we are talking about y versus t, and my system will going to start from here to here. Suppose this is initial point and this is final point. From how many paths we can go from 1 to 2?
So many.
So many, infinite number of paths. Okay, infinite number of paths. So there is infinite number of paths. We can go from 1 to 2 from here. We can go from 1 to 2 from here. We can go from 1 to 2 from here. Okay, infinite number of paths is there. But look at what will be the real problem. The real problem is that when we are at the time t is equal to t, my particle can be there, 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 my particle can be there. Is that possible into classical mechanics?
No.
No, never. Never. It is not possible into classical mechanics. In a classical mechanics, you have to always in a unique path. So which path is going to a most suitable for my particle, more suitable for my system? And that answer is given by what? Hamilton's principle. That answer is given by what? Hamilton's principle. So what is the Hamilton's principle? Hamilton's principle defined a quantity called action. क्या define करता है? Quantity called action. You can say A or I, something like this. What is this A? This action is defined as integral of L, that is function of generalized coordinate, generalized velocity, and time dt. This is your action, and that is function of generalized coordinate, generalized velocity, and time. And now, what is generalized coordinate? If your number of dynamical variable must be equal to what? Number of degree of freedom. This is your generalized coordinate. And what is qi dot? This is generalized velocity. So qi dot is equal to dq upon di if I am talking about ith particle. So this is my action. So what is Hamilton's principle? Hamilton's principle is a very, very interesting one and very, very fundamental. What it said? It says the particle will follow only those paths for which action of a system is extremum. The particle will follow those paths for which action of a system is extremum. So if action of a system is extremum, then del A, that means del L dt, or L is function of qi dot, and t dt must be equal to 0. And now, if we are going to compare it with the calculus of variation, what is calculus of variation? The calculus of variation del I is equal to 0, or you can write del variation of f as a function of y dot x dx, that must be equal to 0. Then f is following the Euler-Lagrange equation. Isn't it? So now we are going to compare it. And when we are going to compare it, what I will get? I can replace f to L, y to qi, y dot to qi dot, and x to t. And what I will get? I will get a very fundamental equation, d upon dt del L upon del qi dot minus del L upon del qi must be equal to 0. And this is a very fundamental equation, and that is known as what? Lagrange's equation of motion. This is very fundamental, and this is nothing but what? Lagrange's equation of motion. Hence, it is equation of motion. I want to treat this equation as an equation of motion. That means it must equivalent to what? It must equivalent to what? Newton's law of motion. It must equivalent to what? Newton's law of motion. It's a very fantastic thing. And now we want L such that Lagrange's equation of motion must be equivalent to Newton's law of motion. F is equal to ma. Now we have to find what should be the form of L. Now we recognize this L as Lagrangian of a system. L is identified as Lagrangian of a system, where L is nothing but kinetic energy minus potential energy. So here we can find Lagrangian of a system, and now you can find that if you write your kinetic energy and potential energy, if you can write kinetic energy and potential energy as a function of generalized coordinate, generalized velocity and time, then obviously you can find Lagrange's equation of motion and you can go for Newton's law of motion. Okay. So this is all about beauty of calculus of variation and Hamilton's principle. So everyone is comfortable?
Yes, sir.
Yes, sir.
Okay. So I will extend this discussion into next class, and next class we will go into some more interesting thing, that is generalized momentum, cyclic coordinate, conservation principle, and then we will solve different types of problems. Okay. Just go and revise properly. Thank you.
Thank you, sir.
Thank you so much, sir.
Thank you, sir.
Thank you.
Good night, sir.
Good night. Good night.